Hopefully the green isn't too faint. I'm going to talk about RL circuits. I've made two videos about inductors, and now we're going to talk about or look more deeply into how an inductor affects a circuit with a resistor. So that's what you call an RL circuit. That's what the kids these days are calling it. You have a resistor, inductor, battery of EMF. We're going to look at two cases. We're going to talk about quote unquote charging the inductor, because the inductor can actually store energy through its magnetic field. So we're going to talk about how that happens, when you turn on this switch and you get current flowing like so. And then when you open that switch back up and close this one, we'll talk about discharging. Not really charge, like, discharging the inductor where you get current flowing again at as this thing loses its magnetic field energy that is stored. I'm not going to talk about where this equation comes up in this video, but this maybe you could just, memorize or something, as the kids do these days. U of an inductor, the amount of energy it stores, is going to equal 1/2 Li squared. I'll talk about this more. I'm not really going to use this equation in this video. I'll make a video about the energy of an inductor later, especially when you talk about LC circuits with a capacitor. For right now, let's just deal with this. And when you close this switch, let's say case 1, I guess I'll call it charging. When you close that switch, you're going to get an increase in current. So let's actually just use loop rule. So when this switch is closed, loop rule tells us that the total potential difference is going to equal 0. So the EMF of the battery, that's positive, minus I times R from the resistor, that's Ohm's law, minus, now some of that battery voltage is going to get used up for the induced EMF. So that's what we call the EMF induced. I wonder if it's going to be minus or positive. Let's call it 0. So EMF minus IR, and we know that the EMF induced is equal to negative L. It really should be positive because it's like positive EMF induced, and it would end up being negative di dt equal to 0. So if my current is increasing, this term will be negative, which makes sense. That does make sense because the induced EMF is negative. So as you go through, you would have a drop in potential. Now let's just solve this differential equation. This is just like charging a capacitor. So I'm gonna move these two terms over here, so I get negative L. Let me erase it, make this better. Negative L di dt equals IR minus EMF. So I can divide both sides by R. So I can get negative L over R di dt equals I minus EMF over R. So now I can do my separate, integrate, celebrate. Get all my I's on one side, get all my DT's and other stuff on the other side. So if I multiply by the reciprocal on that side and divide here, I essentially get di over I minus EMF over R is equal to negative R L dt. Now I can just integrate. So I can integrate this side and integrate this side. What are my bounds going to look like? Well, I'm starting with 0 current, right? Like the instant I turn on my switch, there's no current. Starting at 0 current, and then I'm getting to some amount of current I. And I'm really doing I as a function of time. I'll call it I for right now, why not? So I'll call it I. And my bounds, hopefully this makes sense. We're going from 0 to t, right? Whatever time I'm looking at after I close the switch, that's when I'm finding the current. So this is, hopefully you recognize, this is natural log. So natural log of I minus EMF over R, and my bounds are I to 0. So when I'm doing my fundamental theorem of calculus, remember I'm plugging in 0 as I. So I end up getting minus ln negative EMF over R. This is going to be Plain old simple negative R over L times time. Now I can use my difference of logs property, I minus EMF over R over negative EMF over R. Hopefully this is not a terribly, forgotten derivation. I can take both sides to the power of E. So then I get I minus EMF over R over negative EMF over R. I'm laughing because I hate writing EMF over R. I guess I could call it max current, but we'll talk about that in a second. EMF, or E, sorry, times negative to the negative R over L times time. So now I just have to multiply and solve. And I'll hopefully this algebra isn't like anything crazy. You get EMF over R minus EMF over R, E to the negative R over RL, R over LT, or I equals EMF over R, 1 minus E to the negative R over LT. Love doing derivations on this channel. That's the current as a function of time. So you can see when you take the limit as t approaches infinity, e to the negative infinity would equal 0. 1 minus 0 is 1. So the limit as t approaches infinity for I of t will simply equal EMF over R. So after a really long time, the induced EMF through this inductor is 0, and my R, basically all my battery EMF goes to the resistor, and you get your max amount of current EMF over R. And yeah, hopefully that was all fine and dandy. Now let's do it for, and I guess I should talk about also the time constant. So time constant, tau, that happens, when does that happen? That's when it's 63. Do I have a calculator on me? I always like, it takes me a second to brush up on time constant. It happens when you have 63% your current, I think. So in other words, if you have 1 minus 1 over E, right? So 1 minus 1 over E times your max. Yeah, this should be roughly 0.63, I think, times I max. That's what I meant by rewriting EMF over R as I max. That's the max amount of current you'll get, insured by Ohm's law. So to get that, you really need to get e to the negative 1. So you have to cancel out that RL, so you just get negative 1. So the time constant will equal L over R. If you have a larger inductor, it'll take more time to get 63% of your current max, because inductors oppose change in current. So you're gonna have to, it's gonna oppose change, and it's gonna make it, you have to wait longer to get your max essentially. Or if you have a bigger, if you have a bigger resistor, it's kind of interesting. If you have a bigger resistor, I guess it'll take less time. Why? Ooh, I didn't think about that. If you have a bigger resistor, if you increase the resistance, it'll take less time. I think my gut instinct is because you have less max current. I'll think about that some more. Interesting. But yeah, that's the idea of a time constant. You've seen it with capacitors. Now let's do discharging, quote unquote discharging. I don't know what else to call this. So now if you do your loop rule again, so like this. Now if you do your loop rule, you have essentially the potential difference across this resistor. So, let's see if this works out. Minus IR plus L di dt. I know it's going to be positive because my current will end up decreasing, so this will be negative. So when you have your negative L di dt, it becomes positive again. So this one's not too bad. You could say L di dt equals IR, or in other words, di over I is going to equal R over L dt. Integrate both sides. What are our bounds going to be this time? Now this time I'm going for my max current, which was before EMF over R, and then I'm going to some amount of current I, and I'm starting at 0 going to t. So I get ln I minus ln, I'll call it I max, the initial current, that's better. I don't know why I'm so against using I max, I don't know. RLT, you can do your difference logs, you get ln I over I initial equals, RL to the t. Then you're going to take e to the both sides, and you end up with I equals I initial e to the negative. Oh, I messed up somewhere. Oh, something's supposed to be negative. I messed up somewhere. Where did I mess up? The current will decrease. Huh. Maybe I don't make it positive. Maybe I leave it as negative because even though it's decreasing, like the negative takes care of itself. Yeah, I think that's, yeah, okay. So you would leave it as negative LDI dt because even though it's like because then it would be like the magnitude of change. Yeah, you leave it as negative. I'll think about a better explanation. So it makes sense in my head. I just can't come up with a good explanation right now. A story of my life. So this would be negative. This would end up being negative. That would be negative. Then you get negative RL times time. Yeah. Same deal. This is the same time constant. This is when it's 63% of its original. Or no. When it's 37%. So when it's 63% almost done, I guess. Hopefully this video made some sense. I know it was a little scatterbrained. I'm not too familiar. Like I read up on inductors. I still have like more learning to do. It's like to fully grasp, like to fully understand them. I encourage you to do the same. Pick up textbook, read, learn about the wonderful world of RL circuits. Thank you for watching.